This is ELC111, Introduction to Electricity, and this presentation is on diodes. Now, the official or correct term for these semiconductor devices are junction diodes, but everybody in the field really simply refers to them as diodes. Diodes are made of a PN junction, as shown in Figure 1. And these are a two-terminal device, and the terminals are identified as being the anode and the cathode. The anode is the terminal connecting to the P-type semiconductor material, and the cathode is connected to the N-type semiconductor material, as shown in Figure 1. The schematic symbol for a diode is also shown in Figure 1. And note, looking at the schematic symbol, the arrow points towards the N-type material. And a pictorial of a physical diode is also shown in Figure 1. Note that one end of the device is identified with a band, and this band denotes the cathode terminal. And the way to remember this is that that band correlates to the line on the schematic symbol, the cathode. Now, when we discuss diodes and diode circuits, we need to first define biasing. And biasing is simply the application of a voltage that controls the operation of a semiconductor device. And biasing can either be forward or reverse. Figure 2 shows us a forward biased PN junction. And to be forward biased, the positive of the voltage source is applied to the P-type material, and the negative of the voltage source is connected to the N-type material. And what happens when we forward bias this PN junction is that the positive potential repels the holes in the P-type material. Remember, the P-type material has holes and the N-type material has free electrons. And since like charges repel, having a positive potential on the P-type material pushes the holes away, pushes the holes towards the depletion region. And of course, with a negative potential on the N-type material, the free electrons are repelled from this negative potential, and it pushes the free electrons towards the depletion region. And what happens is that, as you can see in Figure 2, the depletion region becomes narrow. And if the potential difference of the voltage source is great enough to overcome the barrier potential, and the barrier potential, you recall, is the creation, or is due to the creation of ions on both sides of the depletion region. If we overcome this barrier potential, which is approximately 0.7 volts for silicon, then we'll have current flow through that depletion region. And of course, we will always have a voltage of 0.7 volts dropped across the depletion region. Again, this is due to the creation of the ions on both sides of the depletion region when we have a migration of free electrons to fill holes in that depletion region. Now let's look at an example of a forward biased diode circuit. So we see a source voltage of 10 volts. This is connected with positive on the anode of the diode. And in series with the diode is a resistor with a value of 100 ohms. So in this circuit of figure 3, we see that the diode is forward biased, therefore the diode will conduct, current flow will flow in the circuit. So first off, we'll make use of Kirchhoff's voltage law, which says that around any closed loop, the sum of the voltage rises and drops must be 0. So we know that the voltage across the diode and the voltage across the resistor must add up to the source voltage, 10 volts. So to find the voltage across the resistor, we take V source minus the voltage across the diode, 10 volts minus 0.7 volts, gives us a voltage drop of 9.3 volts across the resistor. And Ohm's law tells us that the current flow through a circuit can be calculated by finding the voltage drop across the resistor divided by the value of the resistor. So the current flow through this circuit will be equal to 9.3 volts divided by 100 ohms gives us 93 milliamps. And again, the circuit of figure 3 is a simple series circuit. Whatever current flows through the resistor has to flow through the diode, has to be supplied by the source. So the current flow in this series circuit is 93 milliamps. Now in figure 4, we see an example of a reverse bias diode. Note there's the negative potential is applied to the p-type material, and the positive potential of the voltage source is applied to the n-type material. And again, remember the p-type material is filled with holes, the n-type material is filled with free electrons. Excuse me. So remember that unlike charges attract, so with a negative potential applied to the p-type material, these holes are pulled back away from the depletion region. And with a positive potential applied to the n-type material, these free electrons are pulled back away from the depletion region. And note in figure 4 that the depletion region has become very wide. So this depletion region acts like an insulator. No current flows through the p-n junction, and the voltage across the diode will be equal to the source voltage of the circuit. Now, just like an insulator, if we apply too much energy to an insulator, or to, in this case, a reverse bias diode, that we can actually get conduction through the device. Now, the amount of voltage that will result in current flow through the depletion region depends upon the diode. And this voltage could be 50 volts, 100 volts, 200 volts, 500 volts, depending upon the construction of the diode. But understand that if we apply too much voltage to a diode, that it can conduct, and in this case, the diode will be damaged and or destroyed. So let's look at an example of a reverse bias diode circuit. Figure 5 shows us a circuit with the positive potential of Vs connected to the cathode of the diode and the negative terminal connected through the resistor to the anode of the diode. So this diode will be reverse biased. Now, assuming that 10 volts is within the limits of the diode, we'll assume that the current through the circuit is 0 amps. And Ohm's law tells us the voltage across the resistor equals I times R. 0 amps times 100 ohms gives us 0 volts across the resistor. And again, Kirchhoff's voltage law tells us that around any closed loop, the sum of the voltage rises and drops must be 0. So if we have 0 volts across the resistor and a source voltage of 10 volts, we know then that the voltage across the diode, positive to negative as shown, must be 10 volts. So with a reverse bias diode, no current flows and the source voltage is dropped across the diode. Now, the most common application for diodes is to convert alternating current to direct current, and this is called rectification. And figure 6 shows us a simple half-wave rectifier circuit. Now, we look at the source voltage for this circuit. It's simply a sinusoidal waveform with a peak value of 10 volts. During this positive half wave, from here to here, the voltage source is positive to negative. The diode will be forward biased and we will have current flow through the resistor. Now, during the negative half cycle, from here to here, the voltage source is negative to positive and the diode will be reverse biased. No current will flow through the circuit, and of course all of the source voltage is dropped across the diode and the voltage across the resistor will be 0 volts. So we see in the sketch of the rectified waveform across VR, during the positive half wave period, the diode conducts and the voltage across the resistor is 9.3 volts. That's 10 volts minus the 0.7 volts dropped across the diode. And during the negative half wave, from here to here, no current flows in the circuit. And of course, there is no voltage developed across the resistor. So we see in figure 6, we also see what we call the rectified waveform. This is right here. And note that this waveform is positive only. It is a pulsing waveform, but we consider this waveform to be DC, direct current, because current flows in one direction only. So what we have to do, or what we can do, is to connect a capacitor in parallel with the resistor, and this will smooth out that pulsing waveform. So in figure 7, we see a filtered rectifier circuit. Again, we have a capacitor C connected in parallel with the resistor. And you can see, of course, in figure 7 that it has smoothed out the resistor voltage quite a bit from the previous diagram in figure 6. Now what happens is, during this positive going portion of Vs right here, the capacitor will charge up to whatever that peak voltage is. So the capacitor charges up to 9.3 volts, positive to negative. Now, as the source voltage starts to decrease, now the diode becomes reverse biased, because I have 9.3 volts on the capacitor. Since the source voltage starts getting smaller, I have a positive to negative voltage across the diode. The diode stops conducting and the capacitor discharges through the resistor. So note, from right here to right here, the capacitor voltage, which is equal to the resistor voltage, gets smaller because the capacitor is discharging. Now, somewhere around this point, the capacitor now becomes forward biased, and of course current will flow through the diode and charge the capacitor up again to a peak value of 9.3 volts. Then as the source voltage gets smaller, the capacitor becomes reverse biased, and the diode becomes reverse biased, and the capacitor discharges again through the 100 ohm resistor. But looking at the sketch of the filtered rectified waveform in figure 7, note that this resistor voltage is fairly constant DC voltage. And this is essentially all you have in an AC to DC converter, such as the little black box you plug into the wall that you plug your cell phone or some other electronic device into. It is simply a rectifier and a filter capacitor. Now, LEDs are light emitting diodes. Now, with the junction transistor we looked at in the last examples, the energy that's released when electrons fall into a valence shell, when electrons go through the depletion region and fall into the valence shell of a atom, these electrons lose energy. And in a junction diode, this energy is lost in the form of heat. But if we were to use different dopants, then the energy is given off as light. And this light can actually be visible light, or it can be non-visible light, such as infrared light. Now, the dopants used in an LED determine the color of the LED. It's not the diffuser or the plastic lens of the LED. However, they do typically put a red diffuser on a red LED, a green diffuser on a green LED, but it's not the diffuser or the lens that determines the color of the LED. It's actually the dopant. Different elements give their energy up at different wavelengths. For example, with a red LED, the dopants are aluminum, gallium, or arsenic. We can construct a red LED with gallium, arsenic, and phosphorus, or we can use gallium and phosphorus only. Now, since different elements have different electron volt values, then the voltage dropped across an LED is greater than 0.7 volts. For example, a red LED, when the current through the LED is 20 milliamps, the LED will drop anywhere from 1.8 to 2.1 volts. And in figure 8, we see the schematic symbol of an LED. It's simply a diode with two arrows leaving the component to show it's giving off light. And we see the physical component. And note, to determine which lead is the anode and cathode, we can either look at the dome, and there will be one flat side of the dome, and that flat side is the cathode. It somewhat corresponds or correlates to the band on the component. And also the shorter lead of the component is the cathode. Just like LEDs, if we connect just like diodes, if we connect an LED backwards in a circuit, it will not light. Now, one thing that the technician has to do quite often is to design an LED driving circuit similar to that shown in figure 9. Now, an LED will light with current as low as 10 milliamps, but we're going to design, or figure 9 says figure 10, but that should be figure 9. We're going to select the value of the resistor, such as required to have 20 milliamps of current through the LED. Now, again, looking at the circuit of figure 9, we know that the source voltage equals the resistor voltage plus the LED voltage. We rearrange this equation to give us that VR equals V source minus the voltage across the LED. So we calculate the voltage across the resistor to be 7 volts. And Ohm's law allows us to calculate the value of resistance required when the voltage across the resistor is 7 volts and the current flow through the resistor is 20 milliamps. We calculate a value of 350 ohms. The closest standard value of resistor is 360 ohms. Now, understand the reason for this design work is if we look at a graph that shows us current as a function of voltage through this LED, that this graph will look something like this, and that's actually a pretty good job. And when the current is 20 milliamps, the voltage across the LED will be approximately 2 volts. Again, they tell us we're given that the voltage across a red LED ranges anywhere from 1.8 to 2.1 volts depending upon the dopants. Now, if we don't have the resistor R in this circuit, if I were to apply 9 volts directly to that LED, that 9 volts on my graph is somewhere up here. And what you have to think about is the fact that the diode, or the LED, the LED has to operate somewhere on this curve. This curve gives us graphically all the possible operating points for that LED. Now, where is this line going to intersect this vertical line here of 9 volts? And of course, it would be at some point where the current through the LED would be too large for the device, and the device would be destroyed. So we have to have the resistor R in this circuit in order to limit the current through the LED, or if you want to think of it another way, we have to have the resistor R in the circuit so that we can have some place to drop 7 of the volts, 7 of the 9 volts that is applied. So in this presentation, we looked at the PN junction used to construct a junction diode. We looked at the diode when it is forward biased. The depletion region is narrow, and the diode will conduct or pass current provided that we overcome the barrier potential of 0.7 volts. We looked at an application of a PN junction diode being reverse biased, where the depletion region becomes very wide and acts like an insulator, and no current flows provided we do not overcome the breakdown voltage of the diode. We looked at an application of a diode to convert alternating current to direct current, which is called a rectifier. And then we looked at placing a capacitor in parallel with the resistor to smooth out the pulsing DC voltage, the rectified waveform. And then we finished by looking at LEDs and discussed the fact that the color of an LED is determined by the dopants used in the semiconductor material, or the dopants added to the silicon in the semiconductor material. And that, and then we finally looked at the design of a simple LED driving circuit where we select the value of the resistor R in series with the LED to limit the current through the LED.